Greetings everyone, welcome to Side A, Side B. In this video, prove the Pythagorean Theorem of geometry. The overall plan, develop a line of thought supported by definitions, postulates, corollaries, and theorems. So what's in our toolbox? How about straight up algebra and geometry? Coming up shortly, we'll see the usefulness of the triple angle theorem of similarity, which we just proved, leads to unifying two triangles, the first major step in the proof. On that note, a first step discussion on what we want to prove. The Pythagorean theorem is well known, but in case it's not well known for anyone, let's do some examples. First, a brief historical summary. While the Pythagorean theorem is named after the philosopher Pythagoras, who was born around 570 BC, strangely enough, there's no definitive proof that he was the first to prove it, or even to discover the relationship. Evidently, the theorem was known in various forms in Babylon, even before Pythagoras' time. It's speculated he and his followers popularized the theorem by simply providing a proof, which helped to spread its recognition. It's typically written in the following manner: a squared plus b squared equals c squared. It only works for right-angled triangles, noted by the yellow. It's obvious. A and b are the two sides. C is the hypotenuse. However, a and b can either be the vertical or horizontal line. It doesn't matter. If we want to isolate c, we have to use the idea of the inverse operation. The square root operator is the inverse operation of squaring a number. This means if you square a number, then take its square root, or vice versa, you end up with the original number. Sometimes it's easier to consider the square root as a power of 1 over 2, which it really is. So, vice versa, if we square root a number, say 5, then square it, we'll end up with the number 5. Upon taking the square root of both sides, c is now isolated. But that's as far as we can go in the blue box. We are done. Then again, on the left-hand side, it's tempting to apply the square root individually to each term of the sum, but mathematically illogical. If you did that, you wouldn't hear the end of it from Spock. Let's do an example with all the values populated. We have a equals 3, b equals 4, and c equals 5. Then, 3 squared plus 4 squared equals 5 squared. Is that true? Let's go through it. To solve, we need to square root both sides. Then on the left side, apply the squares to the numbers. On the right, the square root cancels the square by the inverse operation. Nice. Then, sum the numbers, which equals the number 25, which is 5 squared. Again, the square root cancels the square by the inverse operation. Since the left and right-hand side equal each other, the values hold true. But what if we crossed the illogical line? If we applied the square root individually to each term on the left, we'd get 3 plus 4 equals 7. Obviously, these values do not hold true. This time, if we let c equal x, let's solve for x. Square root both sides, follow the same steps to get square root 52 equals x. Then we can rewrite the number 52 as a product, 4 times 13. Which is nice, because the number 4 can be written as 2 squared. However, this time we can apply the square root individually to each term if they make a product, which gives 2 times square root 13 equals x. This last example involves solving for a equals x. Then it's set up in a similar manner, but this time we have to subtract 8 squared from both sides. See that? To isolate x, do as before. To get x equals square root 36, which is just x equals 6. Strangely enough, there's really no way to check our work. except maybe sub in x equals 6, but we know 36 plus 64 equals 100, except maybe, what's the famous phrase? As it were, the proof is in the Pythagorean pudding theorem recipe. Let's begin. Welcome back. The proof is in the pudding. Okay, thanks for that. Maybe the proof is in the recipe though. On that note, to simplify, we actually want to prove the Pythagorean theorem in the white box. The theorem states, in a right triangle, the square of the length of the hypotenuse is equal to the sum of the squares of the lengths of the other two sides, or legs. This relationship is expressed by the formula, which we said already, where C represents the hypotenuse and A and B represent the sides. Suppose we are given a square named the Pythagorean square, or it could be called the Babylonian square, labeled as the following, and then line C bisects angle A and angle C. Next, a rotation which makes the following triangle with side A adjacent with side A. Now we state ABCD is a square. By the definition of a parallelogram, essentially all four sides equal each other. Side A equals side B, which makes side A, side B parallel with each other. The same can be said for the other two sides, which makes angle A and angle C right angles. Next, we have line PX bisects angle DAB and angle DCB. Then we make a rotation so that side A is adjacent to side A. Now we can confidently state triangle QKC is congruent to triangle PKC by the side angle side postulate, because we are given angles B and D are right angles, and sides B and A equal each other. Nice. Next, we know angle C is a right angle, and the angle bisector makes the complementary angles X and Y. But then, as it turns out, the rotation preserves the angle C as a right angle because X and Y just traded positions. By the CPC-TC theorem, all the corresponding sides and angles of the triangles that we just mentioned equal each other. Now consider triangle PBX. We have angle B equals angle C. Angle P equals angle Q. Since angle X and angle Y are complementary angles, and angle P and angle Q are complementary angles, which are right angles, and all the angles are bisected, which divides an angle evenly, then angle X equals angle P, which means triangle PBX is similar with triangle QCP by referring to the triple angle theorem of similarity, which we just proved, which is very nice because we can inscribe the triangle PBX within the triangle QCP so that line BX is parallel with line CP. Knowing that, we have the ratio equality PB over QC equals PX over QP by Thales' theorem and corollary 2 using invertendo. Make sense? Next, since sides A and B equal each other, we can make the following ratio equality by construction. In column 2, we know PB equals side B and QP equals side B plus side B. Also, QC and PX equals side C. Then, in column 3, making the appropriate substitutions, and then cross-multiply, we solve blue circle 1. We do the same for blue circle 2. Next, in the bottom section of column 3, we have a squared plus b squared equals the same. By blue 2, we have b squared plus b squared. See that? Lastly, by blue 1, 2b squared equals c squared. Since we now have a squared plus b squared equals c squared, we have proved the white box. We're done. Very nice. If that doesn't make any sense, then we strongly suggest to go over the theorems we referenced and then come back. So, is the proof in the pudding or in the recipe? Oh, by the way, happy summer, everyone. An exit at this time, totally logical. Until next video, ladies and gentlemen.